In this video, we're going to look at Newton's method for solving systems of nonlinear equations. And if you recall, for a single equation, to find the zeros of f of x, we could use Newton's method. Which says we do it sort of iteratively. Like this, for n greater than or equal to 1. So we would guess at an original solution. We would take a guess at an x naught, for example, put it into our function, put it into the derivative of our function, and solve this. Then eventually, if we chose the initial point correctly, this will eventually converge to an answer. In other words, you'll just keep getting closer and closer to a number, and that would be our answer. If you would like to review this, you can go to the video link below, which is Newton's method for a single equation. So go ahead and look at that if you'd like to review this. But again, in this video, we're going to look at systems of equations. Now, this time, instead of using this for systems, we're going to use something like this, where this is going to be a vector. And this is going to be our function. So it's similar to what we did before. Once again, this is the n is kind of the step number. So just like before, we have like n, and then we're going to put in the value at n minus 1. And we're going to have our function, and it's going to be evaluated at our xn minus 1, just like it was before. So similar, this is similar, this is similar, this is similar. Now, instead of the derivative in the denominator, we're going to have the Jacobian, which if you recall, the Jacobian is like a derivative, and then we'll have the inverse of that. So instead of having like the reciprocal of the derivative, we'll have the inverse of the Jacobian. And if you forgot how to do the Jacobian, there's a link also below for that. Though you can probably just watch the example and you can kind of see how it works. In fact, let's go ahead and look at an example. Find the solution to this system. And so we have like these nonlinear equations. And so when I solve this, so just like you did with the Newton's method, you want to set these equal to 0 and call each of these your functions. So let's go ahead and do that. That's our first step. And so we can say 4x1 squared minus 20x1, 1/4 x2 squared. Bring the 8 over. Then over here, 1/2 x1, x2 squared plus x1, 5x2, and bring this 8 over as well. And this is going to be like our function 1 and our function 2. So let me call this f1, x1, x2. And this our other x1, x2. And so we want to name this as our capital F. And then this is going to be 4x1 squared minus 20x1 plus 1/4 x2 squared plus 8. And then over here, 1/2 x1 x2 squared plus 2x1 minus 5x2 plus 8 like this. And again, that's our function. And that was the function we were talking about a minute ago, this function right here. And we want the Jacobian of this. As I mentioned, you can look at the link below that gives you the video to review the Jacobian. But like I say, perhaps you can just follow this. So again, remember when you have a function like this, so we have two functions and two variables. And so the Jacobian, in this case, J, when you do this, you're going to take derivatives. And the first row is going to be just using just this first function only. So we're going to take the partial derivative, df1, df2. So the first row will have just the first function. The second row will just have the second function with the partial derivative. And then this first one will be the derivative with respect to the first variable, d1, like this. Then with respect to the next variable, like this. Then when you go to the second row, it'll have the second derivative, the second function only. First with respect to the first variable, then with respect to the second variable, like this. Then just go up here and do these actual derivatives. So go back to function 1 and take the derivative of this with respect to x1. So if we do this, you can see it's going to be 8x1 minus 20. Now there's no x1 here. That's 0, 0. Then do it again, do it to this with respect to x2. 0, 0, 1/2. x2, like that. Now go to the second row. That's focusing on the second function. The derivative of this function with respect to x1. This will be, so that this is almost going to be like constants times x1. So you're going to be left with 1/2 x2 squared. Then over here, +2, 0, and 0. Then the derivative of that function with respect to x2, bring this down, it's going to be x1, x2. And then -5. Like that. So that's how you do the Jacobian, and it'll be the same method no matter how many functions, how many variables you have. So your functions will go each in rows, function 1, function 2, function 3, function 4, etc. And then you take the variables in the columns, x1, x2, if you had more, x3, x4, etc. And so there you have it. So now, again, let's just remind ourselves what we're going to be doing. We're going to be using this. Again, this is going to be evaluated this here. And actually, the Jacobian as well is going to be evaluated at the previous step here. So we're going to have to start with an initial guess. So let's do an initial guess. And this is what you did as well when you did for single equation. You got an initial guess, call that an x0. Now, the only difference this time is we have two unknowns. So our initial guess is going to have two elements. And so now we're going to put these into our Jacobian. And so when we put 0 and 0 here, this is going to be -20 and 0. And over here, put 0 here, that's going to give us 2. And over here, looks like that's going to give us 5. When we put, because those will both be 0. Oh, excuse me, -5, like this. And now for our equation, we're going to need the inverse of that. And you remember, when you calculate the inverse, it's going to be 1 over the determinant. And the determinant in this case is upper left times lower right. Minus upper right times lower left. We switch these two. And change the sign of those two. So we have something like this. And this is actually comes out to be 1 over 100. And let me just write that down. So next, we're going to put 0, 0 into our function. And our function up here was this. When we put 0, 0 in this, you can get 0, 0, 0, 8, 0, 0, 0, 8. So let's do that. So this is going to be, and so for x1, x2, we're gonna put 0, 0 in here. And so this is gonna be for x1, x2. We're gonna get 8 and 8. Like that. Now, again, let's go back and work with this. Remember, this is what we're dealing with. That was our method, except we're starting at n equal 1. And so when we do our equation with n equal 1, we're going to have x1, x naught, inverse the Jacobian, and the function at x naught. So let's plug all those in. And so this over here, our initial guess was x naught. So that's going to be our 0, 0 here. This is our Jacobian we just calculated. And this was our function evaluated at x naught. So again, you see what we're doing here. We're taking, let me just line these all up. We're taking this equation here, starting it at n equal 1. So when n is 1 here, this is 1, this is 0. These are evaluated at x0. And then so we did x0, the Jacobian x0, and the function x0. And then go ahead and calculate that. And when we multiply these out, this is going to end up being minus 100. Then this is going to be what? Minus 40 plus 0. And this would be minus 16 and minus 160. So it's minus 172. Excuse me, minus 176. That gives us minus 176 like this. And then now is a good time that we can go ahead and divide this through. So that's going to be 0.4. And that's going to be what? 1.76. So that's our next guess. That's our next iteration. And now we're going to go through the process once again. Now I won't go through all the steps. I'll just sort of set up what we're going to do next. So the next step will be to take this value and substitute it into everything. So just like we did before, we're going to take this. So this is, this is like step 2 for like n equal 2 now. Put this into the Jacobian. And like this. So in other words, all I did was go all the way back to the Jacobian, put our new values of x1 and x2 in. x1, x2, x2 here, x1, x2 in the Jacobian. And then we would calculate this. And then we'll do the same thing with our function. plug x1 and x2 into our function up here. Like this, once again, putting x1, x2, x1, x2, x1, x2, etc. Then I won't go through the calculation, but we'll just calculate that and then substitute just like we did before, except this time we'll be substituting into the equation with n equal to 2. Then that's going to make this. And I'm not putting in the notation, but again, we're evaluating the Jacobian at this x1 point. Like that. And then calculate that. Now, this gets a little bit tedious if you had to do this by hand. So we'll go ahead and do this using Matlab. So I put this all into Matlab, and let me actually start here. So I did the clear all, and this is the initial guess, or the initial point, how you want to say it. Yeah, maybe the initial guess. And remember, if you put the percent sign, that'll make it just a comment. And then I did a loop, because that's kind of what we're doing. We're calculating each x value, then putting it back in and calculating again. So I made a loop here. Then I put our function in. So again, our function was this up here. So I put that in. And so we have like 4x1 squared minus 20x1 plus a quarter x2 squared plus 8. And remember, when you put in a matrix, we put the square bracket, and then we have the first row, and then the second row separated by semicolon. Once again, we have a half x1, x2 squared plus 2x1 minus 5x2 plus 8. So that's our function. And the next thing we want to put in is the Jacobian, which we calculated previously. And that was this up here. And I just called this Jacob. Remember, when you're using MATLAB, you have to be careful about using I, because it'll often take that as a complex number. They may have changed it by now, but they would usually, it would recognize I as a complex number and J as a complex number. So whenever I do the index, I do like I rather than just I. And then rather than use like a J, I'll do something else, either JJ, or in this case, I just called it Jacob for Jacobian. In any case, so when we enter our Jacobian, remember, for a matrix with 2 entries in the first row, we separate them by a space. So we have 8x1 minus 20, and then have a space, half x2, and then the semicolon when you go to the next row, 0.5 x2 squared plus 2, space, x1, x2 minus 5. That's our Jacobian. And then here's the calculation that we had before. We had like x equal x to the n minus 1 inverse of the Jacobian times our function. And so, of course, remember in computer, you just kind of write it like this, then it'll put the answer back into the original x value. Now, MATLAB will probably give you a warning, say that there's a quicker way to calculate this inverse. So you can do that if you want. You can change it to what they suggest, though I put it here just for clarity, just kept it like this. So now what it'll do, this will calculate starting with a guess of x 0, 0. Remember, this is your x1 value. This is your x2 value when you have something like this. It'll start with 0, 0, calculate, and get that first value we got, which was at 0.4 and 1.76. Then I'll use that to recalculate again. And I have it going up to 10 times. There are a lot of ways you could do this. You could have it go, you could set this for a certain number of iterations, or you could change this for loop and have some stopping criteria. You know, if it gets so close to the answer, you can have it stop. But a lot of times I just will set this as at a specific number. And if I look at the answer, if it looks like it's not converging, I'll just increase this. That's just a very basic way to set up a MATLAB code. You can get much more sophisticated, much more efficient than what I'm showing you there. But that's a basic way to do it. So we'll go ahead and run this. And so I went ahead and put this into MATLAB. I put the exact code that I showed you, except I added one more line here. And this was the line just to print out every step, every iteration. I just put like something like this: x1 is this and x2 is this. And remember, this is the formatting. This is telling you it's going to be 8 digits, and the 0.4 tells you 4 of the digits will be to the right of the decimal point. Same thing here. And then we put that in quotes, and then comma x1, x2. So it's going to print out every iteration. Otherwise, I put everything the same as before. And so let's go ahead and run this again. Remember, if you want to run it, be sure you're up in editor, up at the top here. There's these other tabs. Be sure you're in the editor tab. Then go over here and hit run. And then it prints out. The fact, down at the bottom here in the command window, we have our answers. And notice here, it actually converged pretty quickly. You can see again, our first iteration was 0.4, 1.76. Remember, that's what we calculated by hand. Then the next one was 0.4959 and 1.98. And then 0.5 to about 2. It looks like the answer is x1 is 0.5 and x2 is 2. And notice it converged after only about 4 iterations. Like I said, you can either, in this, as I told you before, I did just 10. You could either do a specific number and then just see if it does converge, or you could put some criteria in there to say, okay, once you have 2 consecutive iterations or within a certain tolerance, you could stop. So that's, you have that there. As I mentioned before, also up here, see, it will tell you that the inverse here I'm using is slow, and you can replace it with what they have here. You can put like so. Let's do it their way. They're saying to do this here. And so let's just go down here and let's actually do it their way. So we change inverse Jacob star F to Jacob \F. And let's see what we get. Go up here once again, hit run. And we got the same thing. Though according to what they say, it's much more efficient their way. Now again, our equations are so small, we're only doing a few iterations. We don't even notice any difference. But what they're saying is that if you do the inverse this way, the way they're suggesting, the calculations would go a lot faster and be more efficient. That'll probably come into play if you have a very big system of equations, and they're very complicated, and you have a lot of iterations. They're saying that this would be much more efficient. Though you can see we get the same answer down at the bottom here.